Were you wondering about the handwriting, Balu, or?
Yes. No, I also find it somewhat laborious and time-taking for taking all those things for the lectures. Right. And I'm just wondering whether by just writing, one can save some time. What do you do? I mean, you can just write it in a paper, or you need to...
No, I just write it on the iPad. So.
Oh, you write it on the... You just have a pen and write it on the iPad.
Yeah, yeah.
Okay.
And that's also useful for teaching. So.
Okay.
Oh, that's better. Hey, oh, that's it.
Yes, good evening. We will start the plenary talk number 15 by Professor Kannan Soundararajan. And I invite Professor Balasubramaniam to chair this session. Please.
Thank you, Professor Vijay Kumar. It really gives me a great pleasure to introduce Professor Kannan Soundararajan. And he is a sound to his friends. And Sound did his undergraduate studies in the University of Michigan, his doctoral studies in Princeton universities, and he joined a professor in Michigan. In 2006, he moved to Stanford. And he is well known for his deep work on the Riemann zeta function, arithmetic quantum unique ergodicity conjectures, unexpected biases in the distribution of primes, and so on and so forth. The honors and the awards being rather numerous, I would not be able to list all of them, but let me just mention the inaugural Morgan Prize, Salem Prize, Shastra Prize, Infosys, Ostrowski Prize, ICM Invited Lecture, etc. He is a fellow of the American Mathematical Society. Oh, I forgot to mention his younger days. He grew up in Chennai and had his high school education in Chennai. It is when I met him, or rather he met me. And when I think of him, for me, he's still a teenage boy in Chennai who met me. And I have been following his phenomenal progress during all these years. And I am really pleased to invite him to give his lecture on the character table of the symmetric group.
Thank you very much.
Back to Sound. Yes.
Thank you very much. Hello, everyone. It's a great pleasure for me to give this talk and also to be introduced by Balu. As he said, I know him from a long time. Now it's more than 30 years. And I owe him a great deal as well, because as he said, I met him when I was in high school, maybe just in middle school, even towards the end of my middle school. And I learned a lot of mathematics from Balu over the next 5 years. He would meet with me every day, every week, and sometimes at his house as well. So I remember very much his kindness and generosity towards me. And I'm very pleased to be introduced by him. So my topic for today is about the entries in the character table of the symmetric group. This is not something that I usually think about this kind of representation theory, but the problem ends up being something about the structure of random partitions, which is closer to things that I think about, and I'll try to explain a little bit at least of some of the ideas behind the proof of this result, that almost all entries in the character table for the symmetric group are multiples of any given prime that you like. So this is joint work with a former student of mine, Sarah Palouse. You can see her picture here. She is quite an accomplished mathematician already, and I think you should watch out for this name in the future as well. So let me say a little bit about what the problem is. So we are interested in the symmetric group Sn, which is a very standard classical object. And it has a bunch of irreducible representations. So representing this group Sn as matrix groups. The number of irreducible representations of Sn is the same as the number of conjugacy classes of Sn. And the number of conjugacy classes of any of the permutation group Sn, you can decompose every permutation into its cycle decomposition. And so the cycle decomposition gives you the conjugacy class. And the number of ways in which you can decompose into cycles, well, that's just the number of ways of writing your number n as a sum of smaller integers. So that's the number of partitions of n. So that's a very famous object in number theory as well. So since this conference is in honor of Ramanujan as well, so the partitions were, of course, the subject of a famous study by Ramanujan and Hardy, who established this asymptotic formula for the number of partitions of n. So there are quite a few partitions of n, e to the root n of them, roughly, but not as large as the size of the symmetric group, which is n factorial. So it's small compared to the size of the group, but quite large in comparison with n. Now, given any partition, there's a classical correspondence with taking this partition to an irreducible representation of Sn, going back to Young. And then, as I said, every partition also corresponds to a conjugacy class in Sn by just the cycle decomposition of permutations. So if you give two partitions, lambda and mu of n, you can study the character, so the irreducible representation corresponding to the partition lambda, and the character of that irreducible representation. So that's the character chi lambda, and you can try to understand what happens to that character when you evaluate on the partition mu, on this, which corresponds to a conjugacy class in the symmetric group. So this is the character table of Sn. So it's a square table of size Pn by Pn, and these are the values that we are going to be interested in. So it turns out that these values are all integers. And of course, these integers have been looked on for a long time, but somehow it's only very recently that there were some biases in these integer values that were noticed by Alex Miller. So these conjectures of Miller go back to 2017. So it's quite recent for an object of such a classical flavor. So Miller did a bunch of calculations on these character values. It's not possible to take n to be very large because the number of partitions grows quite rapidly as well. And then you have to take the square of these values if you want to tabulate all of them. So the largest value he went up to was, say, n is 76, where there are already something like 9 million partitions. And he noticed that if you look at these I guess 10 to the 12 or maybe 10 to the 13 entries in the character table for S76, he noticed that most of the character values were even. So like 87% of the time, you got an even value of the character, and only 12% of the time you would get an odd value. He also did divisibility by other primes and also by prime powers. And the data is not so conclusive in that case. And even this, does this number go to 1 or does it go to some other number just below 1? Was not clear. But say, for example, for n is 38, he computed that, well, there are not so many partitions here, only about 26,000. He computed the probability of being even is about 82%. So it has gone up from 82% to 87%, so maybe it keeps going up. But there's also a substantial proportion of the time that it's a multiple of 4, a multiple of 3, or a multiple of 9, or a multiple of 5. Well, here you might say, well, maybe it's just going to 50%, who knows? And also there's a substantial proportion of the time when the character value is just 0. So of course, if it is 0 a lot of the time, then it's going to be a multiple of 2, 4, 3, 9, etc. So these are the questions that he was led to ask. How many times maybe is the character value 0? How many times is it likely to be even, and multiples of any other prime? So based on the numerical evidence, Miller conjectured that the probability of finding an even value of these characters goes to 1 as the size of the group n, Sn, n goes to infinity. So in other words, if you choose a partition lambda at random and another partition mu at random, so there are p of n squared choices for lambda of mu, if you divide the number of times you get an even character value divided by the total number of possibilities, that ratio goes to 1 as n goes to infinity. And he conjectured that the same should hold for every prime. And I suppose it should also hold for every prime power, but I don't know if he conjectured that explicitly. And previously, Miller had established a kind of a related result that if you choose the representation lambda at random, so that's a partition, but then instead of evaluating it on a conjugacy class, the character on a conjugacy class, if you just evaluate it on a group element, G, then the proportion of the group elements for which the character value is 0, that proportion goes to 1. This is a little bit different from the problem that we are considering here, because some conjugacy classes can be very big and some conjugacy classes can be very small. So it's not weighting each conjugacy class with weight 1, but weighting them with the size of the conjugacy class. So for example, most elements in the symmetric group will tend to have a large cycle. So they will tend to have a cycle on the scale of about n elements. Or if you think of an n cycle, the conjugacy class associated with an n cycle is pretty big. Okay. Now, there are other partial results. A very classical one going back to Mackay and MacDonald, and they noted that if the partition mu is very special, if it's just the partition 1 plus 1 plus 1 n times. So here you're looking at the degree of or the dimension of this representation corresponding to lambda. And that degree happens to be even almost all the time. And this was a fact that was known a while back in the 70s. And MacDonald also knew that if you fix a prime p, then the number of degrees that are multiples of p is also pretty much the probability goes to 1. And in fact, in these cases, they had exact formulas for how many of these degrees are odd or not divisible by p. Then Miller had some partial results towards this conjecture, which were kind of made more quantitative by Marotti, and then there were other results by Gluck, and in certain other situations where you evaluate your character on special kinds of of conjugacy classes. There have been results by Ganguly, Prasad, and Spallone, and others. So there's been some recent work on partial results towards such divisibility things. And what Sarah Palouse and I have done very recently within the last couple of months is that we were able to give a complete proof of Miller's conjecture. So for every prime P, almost all entries in the character table are multiples of P. And moreover, you can actually make it uniform as well. So you can ensure that the first, all the primes up to log n over log n squared, all those primes actually divide the entries in the character table. Almost always. So in other words, if you look at the entries in the character table, either they are 0, in which case they will be divisible by any prime that you like, whatever, or they must be, most of the time, they must be multiples of this big number, so they can't actually be small numbers. So in other words, you can't expect to find a value like 7 in the character table that will only occur with probability 0 as n gets large. Now, our result gives the divisibility by every prime P, but it says nothing about divisibility by prime powers. So we know nothing about how many of these character values are multiples of 4, for example. And another question which is outstanding and left open is how many of these character values are actually 0. We don't know if that's a proportion that goes to 1. Possibly it might be a proportion that doesn't go to 1, or it could also be that the proportion just goes to 0, but except very slowly, one can show that there must be at least 1 in log n character values that are 0. And so if in the range of numerical calculations, if n is only like 70, 1 over log n is not going to be distinguishable from just a constant at that stage. And I should say that just before Sarah and I proved the full result, she had first proved Miller's conjecture for the primes up to 13, but then her proof broke down at that point, and what we did here is to figure out a proof that works for all primes P. So let me try to now explain some ideas of the proof. Many of these ideas are quite classical and I think are probably well known to people working in representation theory, but I just want to give you a flavor of the argument and then to say why these ideas actually suffice to show that almost all the character values are multiples of any given prime. So let me say something about how these character values are computed or how we can think about them. There are a couple of different ways in which we can think of these character values. One of them is this Murdogan-Nakayama rule, which allows you to compute these values reasonably efficiently. Another is a formula of Frobenius. We're going to use both of them. So let me start with this Murdogan-Nakayama rule and tell you what it means for finding values of characters that are equal to 0. So this gives a recursive way of computing these character values. And, so we note that lambda is some partition of n and mu is some partition of n, and I'll give you some examples of how this works. And you want to compute this value, and the idea is to take one part from mu and then kind of somehow take it away from mu and also take it away from lambda in a certain way, and then to give a recursive procedure to compute the character values in terms of the new partitions. So let's say in this example, what you do is you take one part of mu. In this case, all the parts are the same. So you take one part of length 3, and then you try to find what are called rim hooks or ribbons or border strips in lambda of size 3. So these are squares on the edge. So like this would be a rim hook, or this would be a rim hook of length 3. In this case, these are all just actual hooks. So maybe the example is not the most clarifying, but what I want to find is like a ribbon at the border. So that might be a ribbon at the border. It should not have a 2 by 2 square, and it should just be confined entirely to the border. So when you remove it, you're still left with a partition. So in the case of this example, so there are 2 possible rim hooks, like so. And if you remove those 2 hooks, you get 2 new possibilities for lambda. those two partitions left over. And what the Murdogan-Nakayama rule says is that you can compute the character value chi lambda of mu in terms of these new values for new partitions for lambda, and then the partition for mu will be after you remove this first row that you have, the row of length 3. So that's what's communicated in this equation. So you have some number of ways in which you can remove a part from mu, from lambda as well. And then if you count the smaller character values with certain signs plus minus 1, you get these add up to give you the character value for chi lambda of mu. So the case of this rule that is of interest to us is if mu has a part which is, say, so large or in some way distinguished that you're not able to find one of these border strips or border or rim hooks of length equal to that part. If you can't do that, then you can't get started on this Murdogan-Nakayama rule. So there are no possibilities in your recursion. And then the character value must simply be 0 because you have an empty sum. So to make that precise, let me also remind you what the hook length of a partition is. So for example, here's a partition of 19. And the hook length is, if I take any box, I count the number of squares to the right of the box, the number of squares to the left of it, and also count the square itself. And that's the hook length of that box. So for this box, for example, there are 2 squares to the right, 1 square below, so that's 3 squares, and then the square itself, so that gives me 4, and I put a 4 inside that box to indicate its hook length. Now, if you have a border strip or a rim hook corresponding to the square, so if you go along the border, so that would be this hook, this rim hook, and you can see that the length of that rim hook is exactly the same as the hook length that I've put inside the box. So when you examine the number of these hook lengths here, if you can't find a length t inside this hook length, among these hook lengths, then that also means that you will not be able to find any border strip of that length. So for example, if I look at these numbers, I see that the numbers only go up to 10. So for example, so there's no hook length of size 11. So if mu is some partition of 19 that has a part of size 11, then I will not be able to find a border of length 11 in this partition lambda, and therefore chi lambda of mu would just be equal to 0 in that case by Murdogan-Nakayama. So that's what I've written down here. If there's no hook length of size t, then there's no rim hook of size t. And so if your partition mu has a part of size t, then chi lambda of mu would simply be 0 in that case. And a partition is called a t-core if there's no hook length of size t, and also combinatorially this can be shown to be equivalent to having no hook length be a multiple of t. So either way, we have the same phenomenon. And so what Murdogan-Nakayama tells us is that if lambda is a t-core and mu has a part of size t, then the character value chi lambda of mu is 0. Now, the t-cores have been studied in the literature extensively. So if I count the number of t-cores of n, that has a nice generating function, which is closely related to the generating function for all partitions, unrestricted partitions. Now, one famous result on t-cores from the 90s is a result of Granville and Ono. This is just by the way, because we don't need it here. They showed that if you take any t that's at least 4, then every n has at least one t-core partition. We are interested in a slightly different problem. We want to know how large should t be. If t gets larger and larger, then presumably it becomes more and more easy to find a t-core. And we want to know how large should T be so that almost all the partitions are actually T cores. And this is something that's not so hard to compute. So let me recall how Hardy and Ramanujan proved the asymptotic formula for partitions. You can use Cauchy's formula to understand the number of partitions of size n by a contour integral. And if you have to choose this circle appropriately, the radius must be chosen to minimize this generating function that you have. And then you can use the method of stationary phase, and it'll say that there's a small arc with angle around 0, which gives you the asymptotics for the number of partitions. Now the radius, if we make a calculation here, the radius happens to be very close to 1, but it's like e to the minus pi over square root of 6n. You choose that radius and then evaluate this integral, and you get the Hardy-Ramanujan asymptotic formula. So if you want to understand how many partitions are T-cores, one way morally to think about this is to think of the generating function that I gave you before, just compare it with the generating function for all unrestricted partitions with this particular radius. And if the difference in these two generating functions is not very big, if it's always close to 1, then you might expect that most partitions are actually T-cores because there's no difference in the generating function of T-cores and the generating function of partitions with respect to this asymptotic formula. So that's a simple calculation. So basically we want, this is dominated by n equals 1. And so you want t to the q to the t times q to the t to be small. And then this factor, which differs from the unrestricted partitions and T-cores, would be close to 1. And we would say that almost all partitions are T-cores. So you can do a simple calculation here to figure out when this happens. And it turns out that if mu has a part which is very large, so larger than square root of 6n over pi times log of square root of 6n over pi plus this little bit log of 6n over pi. So you can see that this is an analytic number theory talk after all. If this is true, then for almost all partitions lambda, those would all be T-cores, and then chi lambda of mu would be 0. Okay, so now you can ask, how likely is it that the partition mu has a part which is this large? And that again is a classical question. So I've just written that corollary off. If you have a large part, then chi lambda of mu is 0. The understanding the largest part of a partition is a classical question, which I'll go back to. But already this kind of explains for you Miller's result that if you pick a group element at random, then the character value chi lambda of G is almost always 0. And why is that? Because if you take a random permutation, then a random permutation, I explained before, will tend to have one large cycle. It'll have a cycle of length about a constant times n. So if you have a cycle of length, even say n over 10, for large n, that'll be much, much larger than what the threshold that I want here. And so for almost all partitions lambda, chi lambda of G would be equal to 0 in that case. So here, it's useful to note that the cycle decomposition of random permutations is exactly analogous to the prime factorization of random numbers, which is something analytic number theorists would be more familiar with. And we would know that smooth numbers are kind of rare. So finding a number with all of whose prime factors are smaller than n to the 1/10 happens like with probability like 1 in 10 factorial. And it's that phenomenon that I'm describing here. But the story for partitions is a little different. And there's a theorem of Erdős and Lehner that if you take a random partition of n, then the largest part of a random partition is on the scale of root n log n. It's the same constant that I had before, square root of 6n over pi, and then a log of square root of 6n over pi. And then you can make it be larger than that by adding some constant here, and you will have an understanding of what is the probability with which that happens. So if you say, for example, v is 0, then that that event, that the largest part is smaller than this, happens with probability 1 in E. Okay, so most partitions will have a part which is on the size of root n square root of 6n over pi, log of square root of 6n over pi, but this barely fails to meet the threshold that I had before for finding character values being 0, because that was off by this extra bit of log square root of 6n over pi. It's that last bit that's missing. So we're very close to getting many values that are 0, but not quite a positive proportion. This will show that some proportion of 2 over E log n of these character values are actually 0. Okay, but now let me remind you again that our interest in this talk is not about finding the values that are 0, which we don't really understand, but of not just finding values that are 0, but just 0 mod p. So there's something we haven't used yet. And this will be a different way of computing these character values, which is a formula that goes back to Frobenius. You can compute the character value of a representation lambda at a cycle at a conjugacy class mu. So here I'm going to write these partitions a little bit, unorthodoxly. I'm going to pad the partitions at the end with a bunch of zeros. So each partition I'm going to think of as having n parts, but the last few lambdas might be just equal to 0. Okay, and the same for mu. So then the Frobenius formula describes the character value as the coefficient of these powers of variables x1 to xn in a kind of a complicated object. This delta is like a Vandermonde determinant, so the product of the xi minus xj's. So that's some polynomial in the xi's, the discriminant. And then this is another polynomial, so it's a product over the parts mu1 to mu of x1 to xn. And if a part is 0, which normally our parts are all positive, but I've padded up this partition with zeros at the end, then this is just 1. And then if the part is k, which is at least 1, then it's just the power sum x1 to the k up to xn to the k. So there is some polynomial that you can write down, and some coefficient of that polynomial will give you these character values. So that's very useful for finding congruences. And again, this is an old fact, that if you have a prime number p, and if you have a partition mu, you can form another partition mu by taking, if you see that the partition mu has p parts of size m, so you have m plus m plus m plus m p times, then you remove all those p parts and replace it by one part of size pm. Okay, so that's how you pass from mu to nu. And when you do that, the two character values are congruent mod p. And this is simply because if you look at Frobenius's formula, on one side you would have a term of the form x1 to the m up to xn to the m raised to the p, but then you get to, if you expand this by the multinomial theorem, all the cross terms will be multiples of p. So this is just congruent to x1 to the mp up to xn to the mp mod p, which is just the corresponding term that you would have in the partition for nu, which now has one part of size pm. Okay, so now we have an idea for the theorem. You start with the partition mu. Every time you see p parts that are the same, you replace it by one part of size pm, and you keep doing this until you arrive finally at some partition mu tilde. So what's the feature of this partition mu tilde? You get it from mu, and then you end up with a partition which has the property that no part in mu tilde appears p or more times, because if it appeared p or more times, you could combine them and get take it one step further. And it's still going to be true that if you evaluate chi lambda of mu, that's going to be congruent to chi lambda of mu tilde modulo p by the Frobenius formula. And now you can hope that maybe mu tilde has a part which is so large that for almost all partitions lambda, chi lambda of mu tilde is just 0, in which case chi lambda of mu would be 0 mod p. So the idea is that mu tilde should have a largest part, which is larger than the threshold that we want to ensure that almost all partitions are T-cores. So that's the main technical result of the paper. If you fix a prime p less than log n over log n squared, and you start with a random partition mu, and you arrive at a new partition mu tilde by this procedure that I described, then the largest part of mu tilde is going to be appreciably larger than this bound, which is the Erdős-Lerner bound for a typical partition, but I get to multiply this by a small bit, this 1 plus 1 over 5p, and this will be enough because I just wanted to beat this guy by it. I wanted to get something like this plus log of n, and I can even obtain that with this constant here. So in fact, the proof should go up to like log n divided by log n, and that would be kind of the limit of the method. Okay. Let me give you, in the last couple of minutes, a heuristic reason why you might believe that, and just say why the heuristic reason is not quite accurate, but it still gives you some insight as to why that is true. When I move from a partition mu to this partition mu tilde, I get a partition that has each part appears at most p minus 1 times. So maybe in general, if I consider partitions of n where each part appears at most k minus 1 times, that has this generating function. And you can ask, how many of these partitions there are. You can make an analog of the Hardy-Ramanujan calculation and find easily an asymptotic formula for this. 100 years after Hardy-Ramanujan, it's very easy to compute asymptotics of these objects, thanks to their work. So there, the radius of Q on which you operate will be a little bit smaller than in the case of unrestricted partition, smaller by this factor of 1 minus 1 over k square root. And the size of this is a little bit smaller as well, as we would expect. And now if you carry out the analog of the Erdős-Lerner result, you would find that the largest part of this partition is what you get for unrestricted partitions, that would be these guys, multiplied by this object, which is a little bit larger than 1. So this is, so that's a quantity which is a little bit bigger than 1. And so that would suggest that if I restrict myself to partitions where each part appears no more than k minus 1 times, then I would get a largest part, which is a tiny bit larger than this. Okay, so this is exactly the analog of what Hardy and Ramanujan did, and then just doing the same calculation as Erdős-Lerner. So this is almost what I want. So what I want to say is that when I start from mu and get a partition mu tilde, I want this partition to have a largest part, which is a little bit bigger than what you get by Erdős-Lerner. And that's kind of what I seem to be saying here. It's in fact bigger by this factor 1 minus square root of p divided by square root of p minus 1 in that case. Okay. Except that this part is not exactly rigorous. And why is this not rigorous? What I have is the collection, the set of all partitions of n, and mu is a random element in that set. And then I have a map. I have some procedure of starting with mu and then producing a partition mu tilde by combining p occurrences of a part with one part pn. So, and that produces a map from all unrestricted partitions to the set of partitions where each part appears no more than p times. But what is random is this object here. So this is chosen uniformly from this set of unrestricted partitions. That doesn't mean necessarily that the partition mu tilde is chosen at random. So the heuristic that I gave you is just an indication of why you might expect the method to succeed, but it's not a rigorous proof of why this method actually works. So this map is obviously many to one because there are many more partitions here than there are partitions here. The asymptotic formulas are off. This one has a smaller asymptotic formula than unrestricted partitions by this factor of square root of 1 minus 1 over p. But we would then need to understand a little bit more this procedure of starting from a random partition mu and going to a partition mu tilde and understand how that operation works. And then to say that nevertheless, even though the measure is the uniform measure here, still the push forward measure on mu tilde is kind of behaving like the uniform measure on partitions where each part appears no more than p times. So that part is a little bit technical, so I don't want to go into the proof of that. I don't. It's not a very long argument. The argument only takes a few pages to explain, but at the same time, it is kind of a computational argument which you have to believe various parts of the asymptotics that go into that. So instead, maybe let me end by just telling you a little bit about how this correspondence between mu and mu tilde works. And just to say why it's a little bit complicated, but still you can understand it by studying the related generating functions. So what we are doing in this procedure of going from mu to mu tilde, it's easiest if I think of a number k which is co-prime to p, and then I look at all parts of the form k times the power of p in mu, and try to understand what happens to these parts when I go from mu to mu tilde and backwards as well. So suppose all the parts that are k times the power of p in mu, so k or kp, kp squared, and so on in mu, suppose these all add up to k times L. If I combine these parts, the k that's co-prime to p will never change, because if I'm going to replace p multiples of p occurrences of the same part by p times m, so the same part, so the portion that's co-prime to k will not change when I carry this procedure out. So in mu tilde, these parts will combine to form something, and they will also sum to kl. But in mu tilde, no part appears more than p times or more. So if in mu tilde, if I just told you what the sum kl is, then I've actually told you how many parts there are of the form kp to the j. You simply write down L in base p, and the base p expansion of L tells you how many parts you need to have of size p to the j. Whatever the digit, the jth digit in the base p expansion of L, that'll tell you how many parts of the form k times p to the j you have there. So if I tell you what this part is in mu tilde, I basically have told you what mu tilde looks like. But there are many, many possible ways in which it could have come in from mu, many partitions mu from which it could have arisen. And that number is, what is that number? If I gave you a partition mu tilde and I told you what KL is in mu tilde, then the number of possibilities for mu are all the possible ways in which you can partition L into powers of P, and then each partition of that will give rise to a partition mu that will kind of push down to mu tilde in this procedure. So that's the complicated map that we have here. So for every integer k co-prime to p, you have certain multiplicities of this map, and the multiplicities are going to be to look at the partition parts here of the form k times power of p, what they sum up to, and then the number of ways in which you can get that from mu would be the number of partitions of L into powers of the prime p, and then you get to multiply this over all the possible integers k that are co-prime to p. So I have just shown you why that's a slightly complicated object, but it's not so bad to analyze. And just by studying its generating function on the same radius as in the Hardy-Ramanujan asymptotic formula, you can show that the partitions mu tilde that you get in this when you carry this procedure out, for most values of mu, they will in fact have a large part, which is a largest part, which is kind of like what we have here, except that we don't get this constant 1. This is roughly 1 plus 1 over 2k. We don't get a 1 plus 1 over 2p. We get something a little bit weaker, 1 plus 1 over 5p, which is still sufficient for the application to divisibility of these character values. Okay, so that's a kind of a quick sketch of this proof. I think I will stop here with thank you very much.
Let me appreciate you for a superb lecture on the partition functions, which is the one which Ramanujan has worked. And now the audience may be able to ask you questions. And if any of you are interested in asking the question, then probably you can unmute yourself and then try to ask the question to the speaker. If not, probably you can put it in the chat box or something so that the speaker would be able to see and answer your questions. Please go ahead. Are you able to hear me?
Yeah. Yes.
Okay, no problem. Okay, then I was sorry.
Yes. Oh, okay. This is Suri here. I just had a small question. Doesn't really have to do with the prime divisibility, but if I remember right, Miller's paper has something about signs, right? Are the signs also equidistributed or something like that? Is there any?
Yeah, you're right. Miller conjectured also that the signs should be plus minus. That the character values should be positive and negative half the time. Once you remove the zeros, and I don't think there's any understanding of that either.
Thank you.
Hi, Sam. This is Prasad. Good to see you again. Thanks. Great lecture. I have a couple of questions, if I may. The first is, so Sarah's proof worked up to 13 or so, right? So was it a different approach, or what stopped working?
So I think Miller already had this idea that you should combine Frobenius with Murdogan Nakayama and see what you get, but he was kind of skeptical that would actually give you proportion going to 1. And what Sarah noticed was that I think she did a bunch of numerical experiments and found that this procedure actually did produce a large part quite often. And she was then trying to prove that this technical result, which I mentioned at the end, and she had a different approach to proving this technical result, which was basically by looking at small numbers and then seeing how many, like just start with 1 and just see how many partitions there are of size 1, p squared, p cubed, and so on, and how to combine them to produce one large part. And already if you look at the small numbers like 1, 3, and 5, and p is 2, she was able to combine those and say that one of these values, say the powers of 2 or 3 times the power of 2 or 5 times the power of 2 must combine to give you a large part with probability 1. And then she was able to extend that argument to work for all the primes up to 13 by using small numbers. Again, she was using small numbers up to n to the 1/4, and she had a different argument to get the independence of how these small numbers segregate. If you look at that with the powers of p, the argument eventually that she and I wrote up actually kind of approaches it from the other end. You take one large part, which is almost of size root n, and then you multiply that by powers of the prime p, and that turns out to be much more efficient. And then that argument actually works for every prime p. So the ideas are all, the ideas of combining Murdogan Nakayama with Frobenius, I guess, are kind of standard in the field. And then this technical result, she had a preliminary argument which worked for a few cases and then stopped working at 13. And then this randomness is what we were able to show for every prime.
Wonderful. If I may, I just have one more question and then I'll shut up. For the question of asymptotic number of zeros, whether that's a positive fraction. So do you believe this approach works with more technical work, or you need a different?
No, I think it only gives you this 2 over e log n, I think, and I don't see how to improve it. One possibility is to think of, we are doing a very local thing, right? Taking one part and then figuring out how many are t cores. It could be that you could think of several parts in mu and think of, if it's a t core for one of those parts, it would still be done. But I don't know how to combine, T1, T2 cores in that way. I don't know how to do that in dependence. And I also don't know, what to expect. I think Sarah told me that Sean Prendeville had done some more calculations, maybe not looking at every possible character value, but doing some kind of Monte Carlo simulations with larger values of n, and the proportion seems to be going up. So maybe it's not a constant. So it's not clear.
Thanks a lot. Thanks again.
Good. If there are no more questions, I will probably ask the organizers to.
Yeah.
Yes.
Thank you, Professor Kannan Soundararajan and Professor Balasubramanian and all the participants. Thank you. Thank you all.
Thank you.
Tomorrow, the last day of the meeting will start at 9:30 Indian time. Thank you.